welcome on this fine Sunday afternoon. For today I prepared some first Newton's law exercises. First we'll start from some conceptual questions and then we'll go to a little bit more of analysis and a little bit of calculations. You can see the timestamps right here. So yeah, let's go. Question 1. Newton's first law says that an object that is not moving or is at rest, when an object is not moving, another word for that is rest, will stay at rest. So rest. The first law says that if an object is not moving, it remains at rest. Unless we act on it with some other force, it should continue to remain at rest. Also, an object that is moving will keep moving with constant velocity. What does it mean? Velocity is a vector that tells you about the speed of something and the direction. Right? So both matter. And in fact, if some object is moving with no external forces, it will continue to move with constant velocity. So it means that it will be moving with the same speed and in the same direction. Unless, as we said previously, there will be some external force. External force that will either accelerate our object or slow it down, or will basically change the direction, possibly change the velocity in some way. Question 2. Newton's first law of motion is also known as the law of inertia. Question 3. What is inertia? So, inertia is a tendency of all objects to resist acceleration. What does it mean? Well, when you think about it, objects want to continue to do whatever they were doing. So, if an object is at rest, it just will continue to rest, as we just discussed with the first Newton's law. If it's moving, it wants to continue to move. Now, obviously, it's kind of a mouthful to explain. That's why we call this tendency of all of the matter with the word inertia. Question 4. What property of an object determines how much inertia it has? Well, inertia is a tendency of an object to resist acceleration. So basically, how difficult it is to slow it down or speed it up. So let's compare two situations. The first one, we have car with just a driver. And the other situation is we have the same car, but it's packed with people inside. Let's say it's like 5 people, the whole entire family. Which car will accelerate faster? Well, you can say obviously the lighter one. Which one will slow down faster? Well, obviously the lighter one. And that's the case. Mass is a measurement of inertia, or mass is the property of an object that will determine how much inertia there is. The more mass there is, the more inertia an object has. So the more difficult it is to speed it up or slow it down. That's why when you think about like F1 cars, engineers want to make them very, very lightweight. Everything in order to make them accelerate faster and slow down easier as well. Question 5. Which of the following has more inertia? So, as we just discussed, the more the mass, the higher the inertia. So in this case, bowling ball will have obviously higher mass compared to a tennis ball, and the hammer will obviously be heavier than feather. Remember, higher mass equals higher inertia. Now let's go to more analytical questions when we need to calculate something and provide some equations. Question 1. What net force is required to keep an object moving with constant velocity at 20 meters per second? Well, you might say, well, I need some force to push an object, right? Obviously, like I need an engine to push a car or something. Not the case. Unless you have some forces that stop an object, like air resistance or friction, the net force required for just keeping the object moving is 0. Specifically, 0 newtons. We express force in newtons. Question 2. Two forces act on a box which remains at rest. Force 1 acts with 10 newtons to the left. What is the magnitude and direction of force 2? Okay, let's make a drawing. Okay, here is the drawing. So, let's start from what we have given as the information. We know that the box remains at rest. The first thing that should come to our mind is that the net force, F net, is 0, right? So, now let's take a look at the drawing. If the force acting on the box goes to the left, F1 acts to the left, and we know that F net is equal to 0, what's the direction of the other force? Well, we know that F net is 0 means that the forces cancel each other out. So for every force acting to the left, we should have a force acting to the right. And that's the case in this example. Now, let's talk about the magnitude. So we know that the two forces balance each other out. So let's think. If the first force, F1, acts with 10 newtons to the left, and we know that the second force has to balance it out, it will also be equal to 10 newtons. You can think about it, in this case, as the two forces act in opposite directions, you can say that the F net is the difference between them. So F1 minus F2. That's because they're in opposite directions. Now let's just plug in the numbers. So 0 newtons for F net, then F1 is 10 newtons, and F2, let's just keep it as it is, we don't know it yet. Now, let's solve for F2. So because we are subtracting here, we'll flip it to the other side. F2 equals just 10 newtons, which is the exactly same as F1. We know it from the previous analysis. Right, so yeah, that's it of this question. Question 3. An airplane moves at constant velocity. Two engines generate 100 newtons of thrust each. What's the force of air resistance? Let's make a small drawing. So here is the force from the first engine. Let's say Fe1 equals 100 newtons, and the same here. Fe2 equals 100 newtons. Engine 1 and 2. And on the other hand, Fr, let's say R for resistance. Now I think that's a good place to introduce the notation for vectorial sum. So let's say F net. What is F net? We said that it's a vectorial sum of all of the forces. Vectors are usually expressed with the small arrows on top of the letters. So F net equals F engine 1 vector plus F engine 2 vector plus F resistance vector. Now, the fact that we have sum of the vectors doesn't necessarily mean that we're actually adding values. In fact, sometimes it's exactly opposite. Now, what I like to do in this case, I like to introduce some axes, some main axes of the drawing. So let's say that's axis X, doesn't matter. Now to convert my notation from the vectors to scalars, so basically just numbers, I need to take a look what's the relationship between the directions of all of the vectors. So in this case, let's say F net equals what? Fe1. Now I take a look. Fe1 is 100 newtons, but it goes towards or along the axis. It goes along the axis. So it will be positive. Let's say plus 100 newtons. The same is the case for Fe2. Engine 2 also goes along the axis, so it will be positive as well. Now, for the F of the resistance, it goes against the axis, right? It goes to the left, whereas the axis goes to the right. So when it's against, I will have it as negative. Negative Fr. Negative Fr because I don't know the value yet. Now you might ask, okay, but how do I know what's the direction of the axis? It doesn't really matter. In fact, you could put the axis exactly opposite and say, oh, Fe and Fe2 are negative, whereas Fr is positive. It doesn't matter. Why? Because the F net is equal to 0 anyway. So they will add up to 0 regardless of how do you look at them. How do I know that? Well, let's take a look here. An airplane moves at constant velocity. Constant velocity means that F net equals to 0. So I can take a look at this equation and just rewrite it as F net equal to 0. Now it's just a matter of a little bit of algebra, so let's do that. And let's solve for Fr. That's it. Let's say that you decided to put your axis differently, so in the opposite direction, like that. Right, let's say you decided to do that because you like that. So now what? The vectorial notation is exactly the same, so I can just copy that. Vectorial notation doesn't really matter how you state your axis, how do you look at it. Now what will change is the scalar notation. Let me show you. So in this case, let's take a look at the F of the engine 1. FE1 is against the axis. Axis goes to the left, FE goes to the right. So it won't be positive anymore. Now it will become negative 100. The same with FE2. FE2 goes to the right, but the main axis goes to the left. So now it will be again negative 100 newtons. Now the FR, our force of resistance, goes to the left, and also axis goes to the left. As it goes along the axis, it will be positive. I add it. Fnet, again, constant velocity, so Fnet is 0 regardless of the direction. So I can rewrite it. Now a little bit of algebra. Let's solve for FR. So now I have negative 200 in this case. So let's move this to the left side. Remember, whenever you change the sign by adding or subtracting, you change the sign. So yeah, I have positive 200 newtons equals FR, which is the exact same answer as we got in the first example. So it doesn't really matter. You can choose both axes. You can check one with the other one. You should get the same results. Question 4. An object is sliding with a velocity of 10 meters per second along a perfectly frictionless surface. Air resistance acts upon the object with 20 newtons. What will happen? Let's make a drawing. So let's say our velocity of 10 meters per second is to the right. So we are basically moving to the right. Now, air resistance always acts against the movement, right? If you want to go to the right, air resistance will try to stop you and push you to the left. So let's say air resistance go like here. FR. Now, let's think. Okay, are the forces balanced? In this case, we have only one force, right? The air resistance, and nothing else actually. Because of that, this force is unbalanced. So for sure, we know that the first Newton's law does not apply in here, right? We are not at rest, we are not moving with constant velocity. So the first one is for sure not correct. Now, let's take a look. Will it slow down or speed up? Because the force is acting against the velocity, it will slow down. The object will go slower and slower and slower until it reaches full stop. Question 5. Are the forces balanced? A. A SpaceX rocket is accelerating from the ground. Well, accelerating, that tells you that Fnet is not equal to 0. We'll talk about that in future videos, but remember for now that if there is some acceleration, so either we speed up or slow down, Fnet for sure is not 0. So in this case, if Fnet is not 0, therefore forces are not balanced. B. Tesla Roadster is floating through space at constant velocity. Well, constant velocity is a big hint in here. We know that if an object is moving at constant velocity, it obeys the first Newton's law, therefore the Fnet is 0, therefore the forces are balanced. C. A car is driving through a curve at constant speed. That's a tricky one. Let's actually take a look at that and make a small drawing. Okay, so let's say this is our car, let's say it's moving forward, but it will be turning right, or the curve that he follows goes to the right. Now, you might say, oh, okay, constant speed, so yeah, first Newton's law. Constant speed doesn't mean constant velocity. Remember, speed is not equal to velocity. It's not the same. It's not the same, yet these concepts are kind of similar. Constant speed only tells you that the car will travel the same distance over time. That's it. But it doesn't really tell you what is the direction of this movement. And here is the key factor. In this case, even though our speed is constant, our direction is changing. So from here, within the next few seconds, the car will be here, and then here, and then here. So the direction is changing. And remember, uniform motion, if you go back to the first question, is when you have both speed and direction that are the same, constant. If either of them changes, it means that the velocity is changed and there has to be some acceleration. In this case, there will be some acceleration or some force pulling this car towards the center of the curve. It will change the direction of the velocity vector. It will change the direction of the movement. Well, you can clearly see that this force is not balanced. Therefore, the net force will not be zero and the force will be unbalanced. D. A banana is moving in a circular motion in space at constant speed. Well, let's make a drawing again. So this case is actually very similar. Even though we have constant speed, it doesn't mean that we have constant velocity. In fact, again, our direction is changing, our direction of movement. So from here, later it will be in here, and in here, and in here. The direction of the velocity vector is changing. So here, exactly as in the previous example, the speed is constant, but the direction is changing. So the direction of the velocity vector is changing over time. As it's not constant, as velocity is not constant, the net force is not zero, therefore there is some acceleration, forces are unbalanced. Okay, that's it for today. If you have some questions, some problems, either in math, physics, or whatever, or some topics that you'd like to cover, there is a new email, askkevinthetutor@gmail.com. It will be right here, it will be in the description. Send me email. I don't know, if you have something that you'd like me to discuss, to explain, or just any questions, I'll be more than happy to help you. Okay, that's it, and see you next time. Stay curious. I like it. Picasso! Sweet.